Hello and welcome to the NPTEL MOOC on Applied Electromagnetics for Engineers. This is a module where we will discuss some bits and pieces of transmission line that is still left out with the steady state considerations, steady state behavior that we are considering. And we begin by trying to find a lumped equivalent circuit of a transmission line. Of course, we know that a transmission line actually is a distributed circuit, okay, because it has a certain spatial extent which cannot be ignored, but in simulation, especially when you want to simulate a circuit which contains transmission line and other circuit elements, the lumped circuit elements in your simulations, it is better or it is useful for you to consider equivalent lumped circuit for a transmission line so that it can be easily simulated along with the other circuit elements. So, you have a complicated network, then you can reduce that complicated network which contains transmission lines into a equivalent lumped circuit. Okay. There are a few advantages of why, as I said, one would be to help you in the simulation, the other is actually more of a problem, because if you were to retain the complete transmission line behavior, then the simulation of those circuits is fairly involved as compared to a simulation of a lumped equivalent circuit. Therefore, to simplify your simulation and to get some insights which may be reasonably approximate, we normally consider the circuit equivalent of a transmission line. This circuit equivalent, let me remind you again, is only for the case of a steady state behavior at a particular frequency of the source that we are considering. We are considering sinusoidal sources, and for that cases, because the voltage and currents in every place of the transmission line is sinusoidal, this equivalent circuit is okay. Now let us focus on what this equivalent circuit is and apply the concept of this lumped equivalent circuit to understand a small problem. Okay. To begin with, the idea of an equivalent circuit is that I consider a transmission line, okay, which has a certain spatial extent of length L, okay, and the transmission line has a characteristic impedance of Z0. We consider the two ends of a transmission line to be with the plane A prime and a plane B and B prime. What by equivalent circuit we mean is that it can be represented in this particular fashion, where each of these elements which I have written in the blocks are all the lumped elements. Okay. You might rightfully ask, if these are lumped elements, what will happen to the spatial extent L of the transmission line, and we will have an answer. In fact, we will show that each of these blocks which we have written, which we are calling as a lumped equivalent circuit, will contain or they will be function of this length L, except that they will turn out to be just some numbers based on whatever the length that we are considering. To remind you again, we are considering only the sinusoidal sources or the sinusoidal steady state behavior, which means my source is actually a phasor of a particular frequency omega, right, and whatever it has a certain amount of value. Okay. The load that I am considering will also be, not in this one, but we will attach load shortly. The load that we are considering will also be described by an appropriate value of the complex number, which depends on the frequency of the source that we are considering. So, everything is harmonic or sinusoidal in nature. Okay. So, that is what we actually mean when we say that we are considering sinusoidal behavior and we want to find out the equivalent circuit. Okay. In your earlier circuit courses, you might have studied certain parameters. Okay. So, these parameters relate the external voltages and the current. So, for example, if I consider this 2-port network, okay, with current I1 and I2 entering into the port and voltages V1 and V2 measured, there are a number of parameters that can be used to relate these 4 variables. Some of the examples are the Z parameters, the Y parameters, okay. Sometimes you might also relate them with a H parameter, as is normally done for a transistor. Okay. For passive circuits which are represented by equivalent parameters, we normally consider them to be Z or Y parameters. Okay. So, if I want to find out a Z parameter circuit for this, I need to relate the voltages on one side. So, I will have to write down that the voltage that I am seeing from the port 1 here. So, this is a port 1, this is a port 2. Okay. Whatever may be the complex circuit inside, I am trying to represent that complex circuit just by giving you the values of V1, I1, V2 and I2 and relating them by these Z parameters. in terms of the Z or the impedance parameters, we have V1 as Z11 times I1, where Z11 is sometimes called as the sending end impedance, okay, or sometimes called as the self impedance of the port 1. There are all these various names, but for us this subscript 1 and 1 refer to the fact that voltage here is at port 1, current is also at port 1. This is some kind of a self impedance that we are considering. Of course, V1 is not just equal to Z11 into I1, but there is a second parameter which is Z12, in which case the voltage is at the port 1 while the current is from the port 2. Therefore, this would be Z12 into I2. Similarly, we have one more relationship for V2, where V2 is Z21 I1 with obviously the subscripts known to you how to interpret them, plus Z22 into I2. We can in fact condense this notation by writing this set of two equations in terms of a matrix relationship. So, I have in this matrix Z11, Z12, Z21 and Z22 with the currents I1 and I2 being considered as the input. Okay. Just to remind you what it is, Z11 is actually the ratio of the voltage measured at port 1 to the current that is measured at port 1 when the current I2 is set to 0. So, when can current I2 be set to 0, or when we can put I2 equal to 0? When we open circuit that second plane B and B prime, so that no current actually flows through this. The interpretation of other parameters I will leave it to you, they are all very similar. Either you are open circuiting the plane B and B prime, or rather plane B B prime or plane A A prime, forcing I2 equal to 0 or I1 equal to 0, and in the bargain obtaining all the 4 parameters called the Z parameters. Okay. This Z parameters is just a set of 4 numbers for the case of a network which is reciprocal, that is it behaves in the same way as it behaves when you go from B B prime to A A prime as when you go from A A prime to B B prime. Okay. This is satisfied in a simple example of a resistor. It does not matter which way you connect a resistor on the breadboard, right. You can label the resistors as A and B and then connect it as A B, or you can reverse the connections and put them as B A. It simply does not matter, because a resistor is a reciprocal device. It behaves the same way if you turn around their ports or you turn around the connections. It has a symmetry of this particular sort. Okay. These 4 numbers, so in such a case what I wanted to tell you was, in such a case Z12 will be equal to Z21. So, you do not have to represent by 4 numbers, only 3 numbers are sufficient to then represent. One more thing, this Z parameters, as I said, are 4 or 3 numbers depending on the network that you are considering, but these parameters themselves does not give you a unique circuit representation. The representation that I have shown here in this picture is called as a T network. Hopefully the reason is quite simple, it is called as T network because it looks like a T, right. So, there is this block, there is a second block here, and then there is a third block. This block Z12 is connected to these 2 blocks by a common node. So, this is a T network. In you can always obtain another network which is called as a pi network, in which the blocks would actually be in this way. Of course, the individual values of this pi, the blocks will not be the same for the pi and the T network. There is a definite relationship between the two. If you are reminded something of the star and delta transformation, then I think that is what I am trying to tell you that, right. So, this can be considered as a star network, if I remember correctly, and this can be considered as a delta network or a pi network. There is a 1-to-1 relationship between the T and the pi network, but the actual numbers that are there will not be the same. This is quite obvious. But coming back to the network that I am considering, I want to find out what is a T network, and here is a small exercise for all of you who are watching this module. There is V1 here, V2 here in the planes AA prime and BB prime, but the blocks that I have represented are not straight away Z11 or Z12 kind of a thing. It is this block which is connecting to which the current I1 is flowing and connected to the plane AA prime actually is given by Z11 minus Z12. The block that is connecting to plane BB prime is Z22 minus Z12. the block that is the standing block out here is Z12. What I want you to confirm is that by applying KVL and KCL appropriately to these two loops, you should be able to show that this network is exact equivalent or exactly represents this particular matrix relationship where V is equal to Z into I, Z being the Z parameter matrix. So, this you can consider it to be a small exercise. This is just to show that you can represent these numbers in any form that you want as long as you are satisfying the original relationships of V, Z and I. Okay, how do I find out these individual numbers Z11, Z12? Again, I do not have to find Z21 because the transmission line is exactly symmetrical. I can turn around B to A, B prime to A prime, and nothing will happen to the behavior of this transmission line. So, what I am to find out are only 3 parameters, Z11, Z12 and Z22. Let us see how to find out. I will first consider Z11. This is fairly easy to find, right? How do I find Z11? Well, you consider the transmission line here, okay, which has some plane AA prime and BB prime, and then you have to open circuit this particular port, that is BB prime plane will be open circuited so that no current I2 flows through this one. However, here you have to connect a certain voltage source, which again will be a sinusoidal voltage source here, so that you can drive some current I1 into this particular terminals A prime plane. Okay, so you drive certain current I1 and you have a certain voltage V here, and what you are trying to find out is the ratio of this V or V1 to the current I1. That is simply nothing but finding the input impedance of a transmission line which has been terminated in open circuit, okay, and has a length of L with a characteristic impedance of Z0. If you remember what is the input impedance formula, Zin for a length L transmission line was given by Z0 into ZL, which is the load impedance, plus JZ0 tan beta L in the numerator divided by Z0 plus JZL tan beta L. So, this is what the impedance transformation formula that we actually derived in one of the previous modules, and when ZL is open circuited, ZL tends to infinity. In the numerator ZL will be remaining, and in the denominator JZL tan beta L will be present. The Z0 and JZ0 tan beta L terms are gone, okay, and ZL cancels from both sides. So, the input impedance of an open circuited line which is of length L is given by minus JZ0 divided by tan beta L, or simply minus JZ0 cot beta into L, cot being cotangent that I am considering with an argument of beta L. Because the line is symmetric, Z22 is exactly equal to Z11, which means this is also equal to minus JZ0 cot beta into L. Okay. So, we have found these two. Now, what we need to do is to find what is the input impedance. Now, we have found out Z11 and Z22 because of the symmetry. What remains to be found is just Z12. In order to do this one, let us go back to the equivalent circuit. This is the equivalent circuit that we had drawn. It is a little clumsy slide, but please forgive that. What you can observe is that if I were to sort of short circuit here, but if I were to short circuit this one over here and then find out what is the equivalent input impedance, right, I can do that. Then I can do the same set of condition on the transmission line itself. That is, I will short circuit the transmission line here, find the input impedance Zin. Obviously, if these two circuits have to be equivalent, the value of Zin that I find here must be exactly equal to the value of Zin that I find from this left hand side circuit. Let us do that here. You see what is Zin that can be obtained once you short this BB prime plane. You have Z22 minus Z12 block in parallel with Z12 block, and then add it in series with Z11 minus Z12. Okay. So, you have Zin is equal to Z22 minus Z12, which is the block that was there. This would be in parallel with Z12. This entire thing will be in series with Z11 minus Z12. You can find out what would be this relationship and solve for Z12. You might be a little surprised here. I am trying to calculate Z12, but I am trying to calculate that Z12 from Z in. I do not know what is Z12. At this point, I do not know what is Z in as well. However, I have an operational procedure, as I said. I can short circuit the transmission line and then find out what is Z in, equate this Z in or use the value of this Z in into the second equation. So, I will leave this verification that after solving this above expression for Z12, you will actually see that this is equal to square root of Z11 minus Z in, okay, times Z22. I already know what is Z22, I know what is Z11, I do not know what is Z in, I will find out, but once I know all these three parameters, it is very easy for me to find out what is Z12. So, how do I find out what is Z in? Now, you are considering Z in of a short circuited load, right. So, you have short circuited the load, the transmission line again has a length of L, and what is the input impedance for this case? Go back to this impedance transformation formula. Here you substitute ZL equal to 0. So, in the numerator this is 0, and in the denominator the term corresponding to J ZL tan beta L will be equal to 0, and what you are left with after cancelling the Z0 that appears in both numerator and denominator, this would be equal to plus J Z0 tan beta into L. Now, we have all the three parameters that are necessary. You can plug that one inside this equation, find out what is Z12, and in fact, you can see that this Z12 turns out to be, after you substitute for all these values, it turns out to be minus J Z0 cosecant of beta into L. I hope you remember the cosecant formula, right. So, secant was 1 by cos, cosecant is actually 1 by sine, and again I would like you to verify this using the basic trigonometric relationships. Okay. Now, we have everything that is necessary. You can easily go back and construct this T equivalent circuit. You know what is Z11, this is minus J Z0 cot beta L. You know Z12, which is minus J Z0 cosecant of beta L. You put the minus J cosecant of beta L here, and in Z22 again it would be minus J Z0 cot beta L. Z12 anyway you know, subtract the 2, simplify it, and you will be able to write down the T equivalent circuit. What is the use of this? Let us consider a very familiar situation. Okay, we will say more about this one when we talk of connecting ICs or ICs driving loads, inductive and capacitive loads, but at this point do not worry about the genesis of the problem, but let us see how we can apply the knowledge of T equivalent circuit in order to solve the following problem. Let us consider a printed circuit board on which there is one particular integrated circuit. This could be a logic circuit, okay, maybe an inverter or an AND gate. It could be it could be an inverter or an AND gate. This would be driving another load. The load could be an interface logic or an interface bus. It could be just a connector that I am considering or connecting to this printed circuit board in order to take the output from the IC1, or it could be one more IC. For example, I might be trying to find a clock, okay, or might be creating a clock by connecting two inverters in series, and the connection between one IC to the other IC happens over a wire whose length again I cannot ignore, and this can be a microstrip line, for example, acting like a transmission line. Let us consider that this has an impedance of Z0, again lossless, and the input impedance of the IC2 is Z2, whereas the output impedance of IC1 is Z1. Okay. Z2 of course could be complex depending on what kind of input impedance that IC is presenting, but we will consider two cases. In one case, the magnitude of Z2 is much smaller than the magnitude of Z0. In other words, the impedance of the transmission line is much higher than the load to which it is connected. The load impedance for the transmission line is the input impedance of IC2. Okay. So, let us consider this case. I will leave the other case for you to worry about. Okay. What we want to know is what is the equivalent circuit in this particular scenario. So, seen from IC1, what should be the rest of the circuit to be simplified. Again, we will go to the appropriate T equivalent circuit with these three blocks that I have, and then substitute this as the transmission line equivalent circuit, to which we are going to connect the second IC whose input impedance acts as a load impedance for this transmission line, and this has a value of Z2. Okay. So, here you will have a source plus Z1 as the output impedance that can be connected later on in case you are interested. So, let us not connect this anything right now, let us just try to simplify this side of the circuit in order to find what is that IC1 is seeing as the rest of the circuit. These blocks are from the T equivalent circuit of the transmission line. So, this is Z12, this is Z11 minus Z12, this is Z22 minus Z12. Because Z11 is same as Z22, we can define this Z11 minus Z12 as some ZL by 2. So, that I have in this one there is a ZL by 2 as the, this is just a way of denoting this Z11 minus Z12. Okay. So, this is ZL by 2 and Z12 let us denote it by ZC. Later on you will see that these subscripts L and C actually represent inductive and capacitive loads or capacitive reactances, which is what we will discover later on. Okay. We will discover very soon. What is this ZL by 2 that I need to find out? For that I need to find out Z11 minus Z12. I know what is Z11, in fact Z11 is equal to Z22, which is minus J Z0 cot beta L. Okay. If I consider length L to be equal to 0.05 lambda. So, please note that this is actually a very small length of the line that we are considering. Although we say that this is a transmission line, okay, the length of the line that we are considering is only a fraction of lambda. Therefore, this must almost be a lumped circuit, and in fact this is the region where these lumped equivalent circuits actually work very well. The lumped equivalent circuit works very well when the transmission line length is very small compared to the wavelength of the source that you are connecting. Anyway, coming back, if I consider length of 0.05 lambda here, I can find out what would be beta. Z0 we do not really need to do anything here, and substituting for beta and L here, beta in terms of lambda, because beta is nothing but 2 pi by lambda. So, substitute, evaluate this cot, and what you get is minus J 3.07 Z0. So, this is the value that you get for Z11 and Z12. You can find out what is Z12 as well. I will leave this as an exercise. Remember, this is minus J Z0 cosecant of beta L. So, this turns out to be minus J 3.24 into Z0. Okay. So, this is Z12. So, what is ZL now? ZL by 2 is actually, this is just a denoting that quantity of Z11 minus Z12. This turns out to be plus J 0.167 Z0, and you notice that we have a plus J something term over here, and this plus J indicates that for this particular frequency or this particular wavelength, the impedance or this block is actually acting like a inductor, giving rise to an inductive reactance. Okay. So, you have an inductive reactance. So, this is now, this completes all of our equivalent circuit. So, the equivalent circuit would be like an inductor with a value of plus J 0.167 Z0 as ZL by 2. So, this is the ZL by 2 that we considered, and the reactance of Z12, which was minus J 3.24 Z0, is equivalent to a capacitive reactance or a capacitive element. So, this was equal to minus J 3.24 into Z0. Then finally, I have one more inductor or inductive type reactance, which is again ZL by 2, J 0.167 Z0. So, this is the equivalent circuit of the transmission line, to which I can now connect the load Z2 here. Okay. I can connect the load Z2, and I am now trying to wait or trying to find out what would be the simplification further that I can perform. If I do not want to perform the simplification, I can leave this circuit as it is, connect whatever the source that I want to connect. The source would represent the IC1, which is driving this second circuit along with the transmission line, and whatever the result that you get will be okay. However, for this particular case where we are assuming that the impedance of the characteristic impedance of the transmission line is much larger compared to the load to which it is connected, which is that Z2 of the second IC, then let us see what kind of a simplification we will be able to make out. Okay. you can see that there are two elements over here. This Z2 in magnitude is supposed to be very small in magnitude with respect to Z0. Therefore, when you add these two terms, you can kind of neglect this Z2, right. You can kind of neglect this Z2, and when you further, so when you neglect that one, what you get is one inductor or inductive type of reactance of 0.167 Z0 connected in series with minus J 3.24 Z0. Okay. So, this is what you are going to get, and you can find out what would be the parallel combination of these two. Since this is about half of it, I am not finding the exact value here, but I will leave this as an exercise to you to use your calculators to find out what would be the equivalent circuit here. Okay. Once you find the equivalent circuit, you can then add to this circuit what would happen, and then you can obtain the full equivalent circuit over here. And as I said, I will leave this as an exercise because these are just a few simple things that you can actually work out, and when you do and work that particular thing out, what you get will be, so since this is very large, this is very small, I will give you the qualitative answer. The qualitative answer would be that the impedance of the parallel combination will be very close to this, that in series with this one would be the total impedance, and essentially what you will see will be that of a inductor. Okay. So, essentially what you will see that would be of an inductor, and this would be very nearly double of what you get for ZL. So, this actually is the impedance that you would see connected down to the low impedance Z2 that we have connected to the IC2, or this is the IC impedance Z2. The lesson for all this, let us summarize all that what we have been doing so far. The lesson here is that if I consider a transmission line of very small length but very high input or very high characteristic impedance and connect that to a load of very low impedance, then the equivalent circuit or equivalent reactance or impedance that I am going to find will be that of a inductor. It will act almost like an inductor. So, this is something that you should remember. A short piece of transmission line with very high characteristic impedance compared to the load impedance to which it is connected will behave like an inductor. If we ask the other question, that what happens when I consider a piece of transmission line with characteristic impedance that is very small compared to the load impedance over here, you can do that calculation also very easily, because in that series combination the load impedance dominates, that load and a small capacitive reactance of Z12, the parallel combination will turn out to be the capacitive reactance, to which you can add a little bit of the inductive reactance that anyway will be smaller. You will see that the net result when Z0 is much smaller in magnitude compared to Z2 of the second IC, that a short piece of transmission line will act like a capacitor, and it will produce or it will present a capacitive reactance to the rest of the circuit, to the IC1. This short piece of transmission line with very low characteristic impedance connected to a very high impedance load looks like a capacitor. Okay. We will see couple of additional relationships between the input impedance and the various conditions, short circuited and open circuited, in the next module. For now, we will leave at this point to ponder over that what would be the pi equivalent circuit of this transmission line. I will leave this as an exercise to you. Thank you very much.